Thanks a lot. Thanks for inviting me. It's really a pleasure, and thanks for organizing this very interesting workshop. So I guess this is going to be the most engineering type of talk of your workshop, because my work is really to use neuromorphic computing and neuromorphic sensing in applications. So there are many flavors of neuromorphic. Here I just want to define what I mean by neuromorphic. So it's really about understanding biology and to build better technology. Better, not in general, but better technology for those tasks in which biology still outperforms current mainstream digital technologies. And we really go from the from learning from biology and devising hardware and circuit design that emulate some of the computational principles that we observe in biology, up to doing computation and trying to develop applications where we can exploit the advantages of neuromorphic technology. This is kind of a slide that summarizes a little bit which are the main differences between digital and neural systems. And so the idea is to try to understand what is so different in the computation that is done by neural systems from what is done in digital systems, and trying to understand if we can exploit these differences. This is a list that is by no means complete, and by no means very precise. For example, in the digital, it's true, we have largely serial computation, but now there are GPUs, so there's a lot of parallelism even in the digital domain. Nevertheless, the recurrency and feedback connections level that are in the neural systems are very far from what can be possible in the digital domain. The variables of the digital domain are zeros and ones. In neural systems, we have analog variables. In digital, we have fast and precise computing elements that are the transistors. In the neural systems, we have neurons, synapses. We can even go down to molecules, are still slow and, let's say, imprecise computing elements that also change during life. So they're not static. In the digital domain, computation and memory are separate, and we keep having to move data from one point to the other. In the neural system, we have what is known now as in-memory computing. So the computation and the memory are co-localized. Another very big difference that we have in the two domains, and that is really one of the key points of this presentation, is the difference in how we acquire the sensory information. While mostly in the digital domain, you have sensors that are clocked. So every clock tick, a signal is sampled. Whatever signal you can think of, it could be an image from a video camera, or it could be the value of pressure from a tactile sensor. The sensing is driven by an internal clock and not by what happens in the external world. While in the neural systems, you have sensors that are active when something happens, when there is a contact of the fingertip with an external object, when we move and we perceive, we have input from proprioception, or when the light changes in our retinas. Another large difference that I think it's really important, and I think it's the direction, one of the possible directions of neuromorphic that I would like to see and that I started working on, is the fact that in digital systems, and mainly in deep learning and in AI, systems are disembodied. What this means is that we get data and we process data, and These data could be taken, like images taken from the internet, for example, or speech taken, again, from speech recordings. What we do, what animals do, is to actively sense, move the sensors, and depending on how the sensors are designed and depending on how they are placed on the body and so on, the sensor signal changes. And so having the sensors, for example, on a robot that can act in the environment could change a lot what we sense. And it could, for example, improve or facilitate the computation. For example, if you have a camera that moves, then your input data is really difficult to analyze because you have movements, and it's very difficult to disentangle what is caused by the movement of the camera and by what is caused by things moving in front of the camera, objects you might want to interact with. Biological systems have a lot of ways to stabilize the image on the retina, and a lot of ways to use the information about how we move to simplify the problem of removing the ego motion from the inputs that arrive from the eyes. So these are just examples, and this is why in the title of my talk there is the keyword embodiment, because I think it's really important. It's a really important direction for our work. So, as I said, what we tried to do was to take this neuromorphic paradigm and use it to test it and to validate the approach on a robot. Because one of the significances of neuromorphic is trying to solve the same problems that the brain solves. And this is mostly interacting appropriately with the real world in real time. So what we did along our scientific path was to integrate neuromorphic sensing on the humanoid robot iCub. We have vision, we slightly touch on auditory system. We work currently a lot on touch. And then we study how to do computation with this type of sensors and how this can help the robot achieve some of its goals. So since I don't really know if everybody knows about what event driven is in terms of sensing, this is an example from vision. This is the output of an event-driven vision sensor. And what you can see here is the X and Y, so let's say the visual field of the camera, and time. When you see a colored dot in the image, is because there has been a change in contrast in the perceived by a single pixel. So if it's a contrast change from light to dark, it's one color. If it's from dark to light, it's another color. And if multiple events happen within a certain temporal frame, you see yellow because there are both on and off spikes. What you can observe here is that the camera doesn't send any spike output if there's no change, if there's no movement. To get data, you really need to either move in front of the camera or move the camera itself. And when you do so, the information has very high temporal resolution. Basically, every time you move from one pixel to the other, to the next one, you see the movement, and each pixel activates asynchronously. So you have very high temporal resolution, that is coupled with high compression. So if you have a frame-based camera with the same temporal resolution, you have way more data that you send around. You have very low latency because you don't wait to acquire a full frame before sending the information out. Um, and basically, you can observe a sort of continuous movement in space and time of your stimulant, and that's very different from frame-based cameras, where you kind of sample the stimulus, and sometimes you can just miss a lot of its movement because the temporal resolution is not high enough, or you waste a lot of data when the stimuli are constant. So these are all very nice, can give nice advantages in robotic vision, but at the same time, it's a very different representation of the information. We don't have an image, so the traditional approaches of computer vision and of deep learning are not directly implementable. So one of the big questions is, how do we compute with these events? How can we extract relevant information? So there are different possible approaches, and we explored some of them. One is, for example, to look at biology and mm, look at models that somehow capture some of the computation performed in biology. In this case, we were interested in the mechanism of attention, and attention is a very nice example of what I was referring to before, saying that we have a robot, we have embodiment, and basically attention is a way to decrease the computational load of vision, so that you basically have, when you look at something, you only process in high details a very small region of interest. And you do so with your fovea, so the central part of the retina. And you need to move the fovea to focus on different interesting parts of the visual scene. Otherwise, you would need a very high resolution retina all over. You would have a very big eye, a very big optical nerve, a very big head, and a very big body. So to optimize this, what you do is to have a center with very high resolution and you move it. How do you move it? Well, you need a system that tells you where to move next. And that can depend on very many factors. Attention is a very complex mechanism that depends on the properties of the stimuli. It depends on what you want to achieve, on your task. But there are nice models, for example, of how attention is driven by the stimulus properties. So without going into details of these models, what I want to tell you is that we were interested in taking these models that were developed for frames, for RGB inputs, and try to understand if we could implement those with a spiking input. Oops. So this is a model. It's a feed-forward model with, where you use convolutional layers to extract features from the images, and you combine them, and you basically need this nice moon-shaped or banana-shaped filter, as they call it in our group. That's the phone is filter. That basically allows you to select relevant objects in the scene. So not only places where you have high contrast in certain feature maps, but places where you have a potential object, or what is called proto-object. This is kind of brain inspired, because these type of filters and grouping cells in the model have been observed in a monkey visual system. But it runs on images. So can we use event-driven input with these models that are bio-inspired? Well, the answer is yes, we can. And we can reproduce, I don't know why the slide is not going on. Okay, we can implement that on neuromorphic hardware. In this case, we use the Spinnaker that I hope you all know. We can implement, again, the banana-shaped filters, and we can reproduce the behavior of the proto-object model, that is this one here, in response to this very simple stimulus. And here you see the sparking implementation on GPUs and on Spinnaker. And then you can also then run it on more complex stimuli. If the slide moves forward. Okay, and you can also, for example, add depth information using in the original, let's say, frame-based implementation. They use the color image and the depth image from a real sense sensor. We could use events from stereo event cameras, from the left and the right camera. We could use disparity map implementation from the events, and basically give priority to close stimuli that are close by. This one should be a video. Maybe it's too slow to load. I don't know why the video doesn't start. No. Anyways, here you would see Julia, the PhD student who implemented this whole system, moving her hands in front of the iCab, and basically the hands that would be these ones here would appear as very relevant in the scene. So the iCap can move its eyes to focus on these. And for example, what you could do is create a region of interest to then run whatever classification or object recognition algorithm you want, but you only have to do that on a small region of interest. So another method to process visual information from event cameras is to look into computer vision. So what we would like to do is to exploit all the wealth of knowledge that has been developed, for 20 years in the field of computer vision to the stream of events from event cameras. What we don't really want to do is to recreate frames, right? You don't want to go back to having a reconstructed frame. And we would like to exploit that the fact that the data arrive asynchronously and sparsely, mostly sparsely, if you don't have a very cluttered environment, and somehow have an algorithm that runs asynchronously and sends output asynchronously, so that at the end the output would be another event stream that is a lot more informative than the raw data from the camera, because, for example, it encodes for features in the visual field. Now, this is an example to show you how the data representation can influence the algorithm. And the example that I give you is to detect corners in the stream of events. Corners are very informative features in vision. For example, if you want to compute the motion of something, if you have corners, you don't have the aperture problem, so you can compute the real motion and not only the motion that is perpendicular to your edge. And so it's kind of one of the basic computation that is done in computer vision. Now, the first work that we did and other groups did was to, you have the event stream. Every event that arrives, you want to have a data representation. You still need to integrate somehow the information of multiple events from local neighborhoods and local temporal windows, because a single event doesn't carry enough information. So you want a special temporal representation. Then if you update your representation event by event, you can then apply an algorithm This could be, for example, the Sobel filter with the Harris score that decides if there's a corner or not. It's not really important what you have to compute. The problem is that the event cameras don't have a fixed frame. They have an event stream. And the event stream, the number of events that you get depends a lot on the clutter in the scene, on how fast the camera is moving, and on how fast the objects are moving. For the new cameras that have high spatial resolution, if you start moving the camera, then this type of approach, since it depends on the time it takes to compute, depends on the number of events, can get very slow. So we had to devise a method to decouple the computation from the number of events. Without recreating a frame. So what we did is to generate these types of representations where for each event you still have a matrix that is similar to an image. And every time you get an event, you update locally this matrix to update the information content. And the idea is that you don't want to define a temporal window because the temporal window has to change dynamically with the number of events, with the speed of the objects and the speed of the camera and the clutter. Otherwise, you start suffering from motion blur or the information disappears too quickly. And you also don't want to be stuck with a fixed number of events because that creates problem when you have scenes that change with clutter, for example. So basically, the idea here is that every time an event arrives, it updates the local neighborhood, wiping out the old information and updating with new information. But wherever you don't have new events, the information keeps being there. And the idea is that if you don't have new events, the visual stimulus that was there in the past, it's still there. So if I walk in a scene and I stop, I'm still in the scene. I don't have to disappear. And once you have this data representation, you can then run an algorithm as fast as you can and output the event stream with the information that you have computed. We have applied this to many different applications. This is the video for the corner detection, and the one on the left is our algorithm. The other two were state-of-the-art in corner detection that are event by event computed. And you see that when you start increasing the number of events, because you start moving the camera in front of the cluttered scene, you accumulate a lot of delay. We applied this also to the tracking of objects in 6 degrees of freedom. So here it's not only knowing where the object is, but knowing its orientation in space. And that is very important when you want to have a robot that manipulates the object, because it has to know how the object is rotated to plan for the correct grasping. Here, we simplified the problem to a 2D problem, so an object moving very fast on the screen. And the idea is that if you can do it very fast, having a very low latency visual pipeline, you can have a robot that moves and tracks the object and keeps the object in the center of its visual field. And here you see the robot with the event camera looking at a screen. And when you start moving the robot, if you have on the left event camera or on the right a real sense, so an RGB camera, when the object starts going fast, then having the low latency from the event cameras and the visual pipeline allows the robot to be more stable and to track faster objects, while with the real sense, simply the control is not stable enough. We also worked on Okay, there's no hope for the videos here. We also worked on prediction. So instead of doing reactive control, you can, from the events, predict where your target is going. Here we had a bouncing ball and the robot being able to catch the bouncing ball using a prediction with the LSTM network that was still asynchronous. It was updated every time the center of mass of the target ball was moving of a certain number of pixels. And we could show that having this prediction with event cameras is faster than with the RGB cameras, so you could move the robot earlier in a safer way, and so you could solve the task for higher speed of the ball. Here is another interesting application. There was a challenge recently in eye tracking with event cameras. We didn't score very high, but I think it's a very nice problem, and it has a lot of possible applications. And if you can do that online, it's, for example, very useful for human-robot interaction, where the gaze direction is really important, for example, for sharing attention between the person and the robot. If the robot can understand where the person is looking at and can do that online, it can really feel more natural. And it can also have, application in driving safety or psychophysics experiments and so on, if you want to close a loop during the experiments. We also worked with deep neural networks. In this case, the idea was to work on human pose estimation. And you can use, again, this data representation where even if the person stops moving the legs, you can still track or have a representation of the full body. And with this data representation, you can train the system with the available RGB data sets and then port into the events domain. And basically, it's still the same concept. And the concept here is also to basically have a detector that runs at very low frequency, and you can fill the gaps between the detections of the poses at very low frequency, and that's what you want to do. For example, if you have low computational resources and you don't want to use the cloud for the inference, you can fill the gaps in between your detections with the events. You can compute the events of the motion of the joints using the events and fill the gaps and have a more precise tracking of the pose. Wow, so this was kind of a very long wrap up of the what is going on, at least in my group, in terms of event-driven vision. I mentioned at the beginning that we work a lot on touch, and I think it's really an interesting domain that is kind of a bit neglected also in robotics with respect to vision. But touch is really an important sensory modality that it's useful, for example, for grasping and object manipulation. That's kind of intuitive, but it's also very important for safety and physical human-robot interaction, so that the robot understand if someone is applying forces to his own body and, for example, can counteract external disturbances and still stay up and not fall down if someone pushes it. And for safety, if the robot is moving and is not compliant and it doesn't have the sense of touch, then it can break something or damage the robot itself. What you see here is the ICAP robot, and where you see the color fabric. So this blue here and you don't see the fingertips, but here it's fully covered with tactile sensors. And these tactile sensors are 4,000 distributed on the body of the robot. They are also under the foot for balancing and walking. And they are sampled every 10 milliseconds. And if you look at these pictures, really the contact locations are very few with respect to the number of sensors you have. So you basically sample 4,000 sensors every 10 milliseconds, and you send 16 bits for each sensor at that rate. And it's kind of useless because where you don't touch, you're just sending zeros. So in this way, in this case, having an event-driven type of encoding, well, that's pretty useful because you just send less data around and you still send the same information. Plus, you can have higher temporal resolution and a lot lower latency. So the fact that touch is very localized in space and time calls for a neuromorphic implementation of touch. Then you also have the fact that being neuromorphic, you can study how biology processes the tactile information, and you can also have an encoding that is more similar to the real tactile encoding. And there's a lot of work by the group of Silvestro Micera, Giacomo Valle, and colleagues that shows that if you use this type of encoding to give sensory feedback to prosthetic users, the feeling is more natural, and the users can more effectively use prosthetic devices. So let me skip this part. So one of the ways you can implement neuromorphic touch is called soft touch or soft neuromorphic approach. Basically, you take whatever you have on a robot, in this case, the fingertips of the iCab robot, and you have an off-the-shelf clock sensor, but you implement spiking encoding of what you have, doing interpolation and then generating the spikes with whatever model you want. In this case, what I'm showing is a video of the generational spikes on FPGA. The FPGA is on this small board that is usually integrated on the hand of the robot. That generates spikes and sends them to another FPGA that also collects the visual information. In this case, we are implementing what is called sigma delta encoding. So basically, when there is a change in the input, we send an output spike. And here you see the raster plot when Maurizio, who's this guy here, presses on the fingertips. And the neuron address changes because it's different taxes on different fingers. Now, why is this useful? This is useful to start doing experiments to use spikes online on the robot for applications and develop computation. So one example that we worked on was to detect or classify the orientation of bars pressed on a patch of skin. This is a representation of a patch of skin on the iCab robot. We were pressing bars at different orientations, and on this layer, each neuron is selected to a different orientation and fires when the correct bar is pressed on the skin. This was a very simple proof of concept that the system can actually converge, and here you see that in the last layer, a neuron responds to a single orientation. This is the input orientation of the bar over time. This is the this encoding layer, and in the output layer, a single one responds for a single orientation. We can skip this one for sake of time. We also looked at again, here the GIFs are not working. Very good. Here we were implementing braille reading system using the spikes from the fingertips of ICAP. So basically, the braille, is this pattern of bumps, and each pattern corresponds to a different letter. To me, it looks like a spatiotemporal type of example of the MNIST. So it's a very simple data set, but with respect to the MNIST, it has a temporal component given by the fact that you slide the fingertip on top of the letters. That's really interesting to study recurrent networks and the classification of this type of inputs. So here, what you see is a sample output of one of the taxes in the fingertip when sliding on a letter, and here you have the spiking activity corresponding to this, let's say, analog input. You have on spikes when it increases, you have off spikes when it decreases, and with different thresholds, you get different activity. Then we implemented the recurrent spiking neural network and trained it with backpropagation through time. And what we could show is that if you implement this type of networks on a neuromorphic platform, in this case it was Intel Oihi, with respect to a traditional GPU, you have very different numbers in terms of power consumption and energy. Here, I mean, we don't need to go into the details of which were the networks and which types of threshold were used, but what I want you to look at is the numbers. So here the average power is in milliwatts, in tens of milliwatts, and this is in thousands of milliwatts. So there's really a lot of difference in terms of the efficiency of the network. And here, depending on the type of network that you choose, for example, here the best accuracy is with the LSTM on Jetson, so no spikes. You get the best accuracy, but you also get 7,000 times the total power. So for you really have a trade-off, and most of the times you don't need exceptional accuracy, but you might want to have very low power consumption and very low latency. I promise I'm almost at the end of the presentation. So this is kind of the next level. So I said that all the previous experiments were done with soft neuromorphic approach, where we basically have a front end that is traditional digital clock. We interpolate the signal, and then we generate the spikes. Now we really want to exploit the neuromorphic technology. We want to have a sensor that is natively event-driven, without the clock to sample the information, pretty much as we do with the event-driven vision sensors. So we worked on the development of circuits that translate an input pressure into a spike train. And this is what this kind of drawing that I made, pardon me for the very low quality. Basically, the idea here is you have some physical transducer that transduces the pressure into an electric signal, and you feed this electric signal to circuits that model the behavior of neurons. And for example, this neuron would fire a lot when there's a lot of pressure. Now, the GIF is not working, but you would see that if you have less pressure, the firing rate of this neuron decreases. And if you release the pressure, then this neuron gets active, and the firing rate would be proportional to the amount of the release in pressure. Now, here we want to implement the spike encoding of the analog signals from different physical transducers. So the transducers that we looked at are the capacitive one, because it's already implemented on ICAP, and it's already integrated in a full system. So we can do experiments with the robot immediately once these circuits are ready. And also the piezoelectric, because it has the advantage that it's easily integrated on silicon, and, well, not so easily, but it can be integrated on silicon, and you have very high bandwidth that is useful for vibrations that are typical when you do texture recognition. And also, you want to know to have the flexibility to use different types of encoding. So what you see here is a sort of encoding that is similar to a slow adaptive neuron, where you encode the absolute amount of pressure in the interspike interval. But there are also fast adaptive type of mechanoreceptors that only fire when there's a change in the signal. Yeah, that's this slide here. So basically, you have different types of mechanoreceptors in the hairless or leopard skin, so fingertips and palms, and they have different size of their receptive fields. They respond differently to the stimuli. So, for example, you have these fast ones that, as I said, they respond only when there is a change in the stimulus, and the Pacinian as well. While the slowly adaptive ones, they have persistent activity also when the pressure signal is constant. But still, they are event-driven, because if they are not pressed, they don't fire, or they have very low spiking activity. So the question would be which transducer and which encoding. So as transducers, as I said, we use piezoelectric. This is a transistor. This is a cross-section of a transistor where you deposit the piezoelectric material on top of the gate. When there's a force applied, there is a generation of charges that can be translated into different current that flows along the transistor. And you can use these for the fast types of mechanoreceptors. And we can use capacitors. This is the cross-section of a fingertip of the ICAP robot, with a fingernail, with a chip that does the acquisition. Basically, what you have here is this layer of skin where you have two plates of the capacitor, and in between a dielectric. So when you press, the dielectric changes size, and so the capacitance changes. And you have multiple of these on the fingertip. And you can use this, for example, for the slow type of encoding, the slow adaptive. And now I present you the results from the chip that were kind of acquired very recently. We implemented few taxes on chip to test different types of circuits. This one is the layout of the piezoelectric circuit. And basically, the layout is what you send to the foundry, the instructions that you send to the foundry to produce the circuit in silicon. And you have the different elements, you have the transistors, you have this big pink square here with the small pink dots is a capacitor. For example, you have metal wires and so on. And then you get the chip back. It has been produced for the engineers. This has been produced with XFAB 180 nanometers, and it's 700 square micrometers. And this is what you get when you send a signal as input to this circuit that you have on the desk. So we tried sawtooth, we tried sinusoidal waves, and we tried kind of pulses. And what you can observe here is the spiking activity of the sensor, where you have spikes from from the on neurons when the stimulus pressure increases, and from the off when the pressure decreases. And here you have the frequency, instantaneous frequency. So that's the interspike interval between the spikes here, and you can see that it's kind of correlated to the slope of the signal. So it's constant for this one. It's shifted with respect to the sine wave, and you only have the activity during the change of the fast changes of the pulses here. And we characterized it. And basically, what you can see here is that the output firing rate of the neuron, of the on and the off neurons, is somehow proportional to the change of the input force. And you have saturation, of course. At a certain point, the neuron cannot fire faster than a certain frequency, and that depends on the refractory period and intrinsic physics of the circuits. But you can still encode for different slopes with different output firing rates. And what you see here is that if you send an input sine wave, the output firing rate follows, again, a sine wave for the on and the off spikes. And if you fit the sine wave here, basically you can prove that there's a 90 degrees, almost 90 degrees phase shift between the input and the output. And this means basically that the output of this circuit is the temporal derivative of the input. And that's kind of similar to the fast adaptive because they only respond to changes during the change. So we also worked on the capacitive. This is, again, a GIF that is not working, but basically what you can see here is that, the frequency output correlates with the input frequency and not the slope at this time. So basically you have sustained activity that is proportional to the input pressure, similarly to the slowly adaptive fibers. For this one, we have, again, the chip back, but we need to do the experiments, and we are in the process of doing so. So these are simulations of the circuit. So what would be next? Well, I think that the directions where we need to go is, for example, going towards flexible neuromorphic sensing, especially for touch. And we need to work on embodiment. So really trying to exploit the synergies that you can have when you have a robot and sensors integrated on a robot and actions to simplify the problem of perception. And also we need to go, let's say, end-to-end spiking. We still have this, back and forth between, if we want a full application on a robot, most of the times we have this back and forth between the digital system, the neuromorphic system, and its continuous translation. And now there are a few initial proof of concepts of end-to-end spiking robots that are really exciting to see. So this is kind of an example of a flexible type of sensing, and where we want to also put neuromorphic computation on these flexible substrates. And this would be the direction, going to flexible and soft robots, where really there can be a synergy between the body and the computation. So I added this couple of slides to, I think, stimulate a bit of discussion. Where are we now in the field of neuromorphic? And the field of neuromorphic has really a lot of other parts that I didn't talk about. So for robotics, vision, artificial intelligence, and health, we are at proof of concept applications. I didn't talk about the health application, but the idea is that with this type of very low power computation, we could go to edge computing and have computation for biomedical applications. For the neuromorphic hardware, now we have very good quality event-driven vision sensors, and we start having proof of concepts for touch. There's some work on olfaction and audition, and we have large-scale and edge computing devices. For the materials, we have memoristic devices, and now there's a lot of work also in photonics, organoids, flexible organic and inorganic electronics. I think there are a lot of things that are boiling there that hopefully will mature with time and will be more available for developing neuromorphic hardware. In the neuroscience domain, that's also very important for us. We have a partial understanding of mechanisms of neural computation and plasticity. And I think that what we need, and a lot of groups are working on, is to formalize theories of neural computation and plasticity. So from the point of view of a person who wants to develop an application, what we don't have is a formal theory, a method to develop applications. We are developing things and methods, and try to come up with ideas on how to design the networks. There's definitely the need for more theory that supports us. And there's a lot there going on, but at least there's nothing really consolidated, as there is in computer science, Boolean logic, and Turing machines. So this is a slide, and maybe you will not agree with what I'm going to say, but where could we go? Well, for robotics, vision, AI, and health, I think we need to scale up. Oops. I don't know what happened. Everything became black.
Somehow the presentation got lost. Yeah.
Yeah, I'm not stuck. Anyways, I can look at. There's nothing visual to see. I can stop sharing, look at my presentation, and tell you what was written there.
Yes, perfect. We've talked for a bit more than 50 minutes. You wanted me to let you know when you've talked for 50 minutes. That's
Cool. I'm almost done. This was kind of the last slide.
Yeah, please continue. Yeah, that'll do.
Okay. So basically, the idea is to go on one side to scale up the applications on robots, and maybe integrate it with cognitive models of the brain to solve more complex human-like tasks, for decision making, and then for having robots that solve problems and then can accomplish tasks autonomously. And then also there's another direction to go, to extreme edge applications for wearable medical devices. I think these are two very important themes. They're not. I'm not excluding anything else, but to me, these are the two main directions where I would like to go. For neuromorphic hardware, as I said, I would like to go to see things going beyond silicon, for example, towards flexible, sustainable, and biodegradable electronics. And on silicon, for example, that is the most mature part, is I would like to see the integration of additional computational primitives from the neuroscience domain. For example, now we are looking a lot, not me personally, but the community is looking a lot at dendritic computation and multi-compartmental models. So integrating on silicon additional computational primitives that the neuroscience side can tell us are crucial for computation. For the materials, I think we need to integrate more and have something more mature available to the research community. For neuroscience, more understanding and computation and models. And I would really like to see formal theories of neural computation and plasticity in the spiking domain, and programming and deployment tools for consumer level. As we have tools for deep learning and AI, we should develop something also for our community. And this was the last slide. I have a very nice picture of my group because I think it's really important to. I cannot show this. We were all doing the heart sign around the icon. It was really cool. But really, it's very important to me to thank all the people in my group that work hard to achieve these results. And thank you for your attention.